Okay, students, let's get started with our session. This is the last session of the last regular session of the semester. We'll have a little bit of instruction, and then we'll do a little mini review sheet using iClicker, and it's ready to hand out. We'll do that in the last half of class. Are you guys with me or what? I mean, you're right here. You're talking right over the top of me. You're probably Olivia. You're close enough to be on the YouTube, right? So that's not what we want. Yo! Is it? Oh, we got. Oh, okay, good. The microphone has come back on. Thank you. Looked like you wanted to come in here and get some homework or something. It's all right. Good. It's good. Before we get into the probabilistic theory of the wave function and the covalent bond, I want to give you a little bit of a description of the final. So here's what the final's going to be like. It's cumulative, so study everything. Everything that we've studied. And as I've said before, concentrate on the sessions, like the YouTubes, as your priority. You know, just reading the book, you know, I've got annotations in there. There's second priority. You know, our YouTube sessions, our sessions here are first priority. But just reading the book, you know, I got to read the whole chapter. No, you don't have to do that. That's not what, you know, you could do it. I mean, it's nice. But we've skipped a lot of subsections of chapters. So you just got to, you know where to read on stuff. But reading chapters, I don't know. Reading my annotations, though, is good. So it's going to be comprehensive. We have 84 points. Now, here's what I'm going to be doing. I'm going to be doing 3 or 4 calculations for 5 points each, and we're going to be clicking them in with the iClicker. So you have to have your iClicker with you. All right? You have one shot to get those 5 points. And maybe if I analyze them correctly, I might be able to give you some partial credit if you're close, or if you're missing a factor of 1/2 or something. So that means, that's maybe 15 or 20 points. And so that means 60 something Scantron dots. Okay, so the rest of it will be on Scantron, multiple choice. Okay, now the multiple choice on Scantron is going to include some calculations too. But those ones you'll have a true answer mixed in with the multiple choice wrong answer. So you'll at least have something to go by. All right. So you're going to have a bunch of calculations, and some to click in for 5 points, some to click in for 1 point as multiple choice. Be here at 7 o'clock sharp. That's what my plan is. I'm going to try to be here before that. We're the first ones in, so if you're here before, if the room is open before 7, come on in. But I'll try to be up here 6:45, and I know Ray down the hall will let me in. So if I'm in here, just come on in, okay? And we'll just get started as soon as we possibly can. All right, so no cell phones on the test, and we're going to be watching. All right, you have to bring your own calculator. Okay, so one of these jobs. Now, what I don't want you to do is bring a graphing calculator. All right, programmable graphing calculator. No, we had some complaints about them in previous exams, so I'm going to ban those for the final. Okay, but just get yourself one of these babies. Make sure you know how to do scientific notation, and you'll be golden. Okay. And most of you have these, so that's good. But you can't use the one on your phone. I mean, my iPhone has a nice version of this, but you can't use your iPhone, or you can't use your phone at all. Okay, so this, pencil, eraser, clicker, and all the mental preparation you could possibly do. Do not, and just to be your mother-in-law for the next 30 seconds and nagging you, do not stay up all night before the final. Because if you stay up all night before, and don't stay up until 3, right? Get yourself done by midnight or so, and then set your alarm clock. And if I hear anybody come in here late and they say that their alarm clock didn't go off, or that they slept through the alarm clock, or their dog ate the alarm clock, anything like that, that's tough. It's tough toenails. If you get here after the first person finishes, and that'll probably be about 7, that'll be about quarter to 8, 7:40, 7:45. That's my guess. You're toast. You can't take the final. All right. Also, I highly recommend that everybody make sure that you use the facilities before you get in here, so you don't have to make any emergency runs out to the bathroom, because we're going to have to escort you. All right. Because I know a lot of times stuff happens that's not exactly righteous during exams. So now I know you guys are nice young men and women, and you're not going to do that, but we're still going to escort you if you have to do that. So try to get all that stuff squared up. So try not to drink a huge amount of coffee and Monsters stuff on Friday. Okay, and I'm banned for life. I can't drink coffee. The doctor says no, it's bad for your heart, So no coffee for me for the past 6 months, and no Monsters. Can you believe that? Yeah, why bother? I mean, it's no green tea, no nothing. So, anyways, make sure you get a decent night's sleep, 4 or 5 hours, maybe 6 if you can. I know, and I know we're crushed. We're on Friday morning. We don't have much time to get ready. Let's see, 24 hours from now is Thursday morning. We got less than 48 hours, and we got instruction today. You want to bring up now, I want to go over something. We've got homework 5 running. Okay, here it is. And it's basically to do a calculation on the homework or on the classwork from Monday. So this is what 24 of you have started it. It's just 2 questions. One of them is to actually calculate, and then the other one is to convert into electron volts. So, I think you guys will do well. 24 of you, raise your hand if you got it if you got all 6 points on it already. Good. All right. So it's a good little workout. Now, okay, switch back to. Now, last time we had that calculation, and what I found was in my spreadsheet, I was going for my spreadsheet, and I had a +2 instead of a -2. So what I had was calculating for a different position than what you guys are calculating. So you guys were right, negative, and I just did it out by hand after class. Negative 12.5 times 10 to the minus 20. So that was righteous. And your homework, yeah, they're already in there. So you guys are banging. And so if you got that one right, you're golden. Now, your homework number 5 is similar. All right. Now let me ask you a little IQ test. Let me ask you a little. We've been talking a lot about this classical model of the hydrogen atom. Those potential energy calculations. Any predictions what you're going to see on the final, maybe? You're going to see a lot of stuff, but just, be ready to do something like this, okay? Now, Now let's get down to homework 5. If you in fact move proton B left and right and recalculate V, you could do it, and that's what you're basically doing on the homework. I give you a set of positions to move B, proton B. Here it's a little closer than it was. On the homework, the diagram was a little further out, but you have a slightly different position. You recalculate it. If you do that, so move it left or right, and then recalculate V, here's what it looks like. Go ahead and make a sketch of this. And this is the classical potential energy curve. All right. And there's a couple things I want to discuss with you about this. It's important. And we didn't talk about potential energy curves like this in 2053, but we'll talk about it now. Right. So this is you recalculating, 30 times or however many dots there are on this diagram. And you can see that I've got my scale. Oh, that's the old scale. It still looks like this. Just go ahead and draw the sketch. Just draw the curve, the classical potential. Forget about those. I'll change that scale when I get when I correct the before I YouTube it. So the potential energy. Here's. Let me get my cursor over here. Here's 0. All right, this is the one. Now this one's supposed to be negative 12.5 instead of this nonsense over here. Okay. So here's 0. All right, that's what we calculated in class. And for homework, you're calculating somewhere between -1 and 2, I believe. All right, so you got a bunch of values along this curve. So if you plotted them all, I mean, if you did a zillion of them, and every half a nanometer or every tenth of a nanometer, it would look like this. Now, let's think about throwing a baseball up in the air. Baseball up in the air, you throw it up in the air, it's going to higher and higher values of potential energy. Okay? Well, on the way down, it's going to lower and lower values of potential energy. It's converting it to kinetic. Right? So that's what we got over here. On the left side of the graph here, the slope of the potential energy curve is down and to the right. And that means that you have a force to the right. So make a note of that. In this, draw a little circle or something over here. In this region, the force between the two systems is repulsive. It's trying to drive them apart. You're trying to drive proton B off to the right. All right? But now look over here. On the right side over here, you have a downhill, and that means that from high potential energy, Cassidy, to low potential energy means go left. So there's a certain distance right here at the bottom of the curve that to one side you get repulsion, to the other side you get attraction. All right? This is standard physics. Okay, now this is the classical picture. We're not talking about any quantum waves yet, but we're gonna. And I want you to totally mesmerize the shape of this curve because of what's coming up when we look at it in not the classical physics sense, not the Newtonian physics, but the quantum physics methodology. So let's talk about that now. All right, Mackenzie. If you, this is the total potential energy. All right, so this tells you that the entire system either wants to split apart. The entire system over here at these distances, the system is going to try to push itself apart. At these distances, it's going to ease itself in. Right, and right here, it's going to. So if you can get them, to this configuration here for B, for proton B, they're just going to kind of sit there. All right, there's not going to be any mutual repulsion. All right, so that's how you. Now this is a many body problem. It's 4 particles, so you really got to do it in three dimensions, which is a little tougher. This is just in one. We're just varying 1 proton. But in the Born-Oppenheimer approximation of the hydrogen atom, this is you only have to worry about the positions of the 2 protons. So let's talk about the quantum waves. All right, now we talked about de Broglie's hypothesis. He said, look, let's treat the electron as a wave and look for constructive interference conditions. And the way it worked out, using H, Planck's constant, and all the normal energy considerations, you know, K, Q1, Q2 over R for the hydrogen atom, very simple. And this is just for one atom. It all worked out at certain orbits, n equals 1, n equals 2, n equals 3. Now, those waves, the guys that came after de Broglie figured out that those waves are physically interpretable as probability density of finding the particle. Now, what do I mean by that? If you have a particle in a box, or if you have Andrew and Brad with the slinky, same physics. There's a standing wave. That's n equals 1. That's n equals 2, the first excited state. You're going to have a high, wherever the amplitude of the standing wave is maximum, you're going to have maximum probability. So there's going to be if this were a quantum system, there'd be a probability of finding it at, you know, about this. This is about a quarter of the way through, and over here a quarter of the way through. So really what you do to calculate the probabilities is square this wave function. But if you have a big bump or a big dip, that's where you're going to have a lot of probability centered. That's how you interpret that, right? So probability density means the probability of locating the particle, you know, in each pixel of length, you know, from one side of the box to the other. All right. Now we don't have a box with the hydrogen atom. We don't have a box with the hydrogen molecule. All right. And this is what the wave function looks like for an isolated hydrogen atom. All right. It's an exponential. Let me move this out of the way. This is the electron ground state. It's exponential. All right. And I started graphing. You know, I don't want to put it at 0. But it's an exponential decay, and it has a distance scale. It's called the Bohr radius, which is a combination of the, you know, H and the mass of the electron and the charge of the electron and stuff. And so what you would do is you would say, all right, the higher amplitude for this is not really a wave, but this is what you would call the wave. You use a wave equation, and this is the solution for the ground state, even though it's not wiggling. Now we're going to look at n equals 2 in a second, and that's going to have some wiggles in it. This one, it just has an exponential die-off. Now this is the radial distribution, okay? And there's no angular variation, right? So this one, all around the nucleus of the hydrogen atom, you know, the probability of finding the electron goes down, down, down exponentially. So way out here, okay, if you square this number out here, you have a very low probability density. But over here, you have a relatively high probability density, right? So you just calculate. So it's like saying, if I have 1,000 electrons, you know, a good 800 of them are going to be between here and the top of this curve, you know, and then down here, for this little segment down here, oh, I might have about 42 or something like that down here. All right. Now you only have one electron, so you can't say that you've got 1,000. Okay. But it's as if that's kind of proportionally how you would interpret it. All right. If you've ever heard of the uncertainty principle, did you guys learn that in chemistry class? Okay. The uncertainty principle. Raise your hand if you heard that in chemistry class. Just a few of yous. How about Pauli exclusion principle? The exclusion principle. Anybody here? All right. So that's all related to this probabilistic interpretation. Now, right, so make a sketch of this. And just a rough sketch is good. There's nothing, I tried to do a really good job with this. So this is the actual function. But I didn't dress up the axes or anything. The horizontal scales in nanometers and the vertical scales in just, generic units. But it is an exponential drop off. Okay, so exponential decay as you move away from the center. So that means the electron is probably going to be really, really close. But now that goes against the whole idea of energy levels, but it still works out pretty nicely. All right, the most probable distance. Because the thing that you don't have here is to get go ahead and make a note, to get the potential energy, you have to multiply the potential energy function, V equals minus KE squared over R, times this wave function, and then times the wave function again. You got to square it. And then you get you get that energy level. Now, here's what the hydrogen molecule looks like. Now, so this is the sum of two ground states. Let me get that. No, I can't do it. So, same distance scale, a little bit shorter vertically. So this is the this is like, this is like this is the sum of the two ground state wave functions, one on the right, one on the left, or one at 0, and the other one out at 0.74. So this is putting the proton B out at 0.74 nanometers. And then you do the wave functions. And it's just simple exponentials. Now, I'm just giving you pictures. I'm not giving you the wave equation. The wave equation is extremely bodacious. So you'd need a ton of calculus and a ton of physics. But the pictures, yeah. All right. Now, down here, this is actually constructive interference, because right down here at the symmetry point between the two nuclei, you've got constructive interference. Now, if we didn't have that, if we had something like this, it'd be really, really small. But out here, at the same point, it's quite a bit higher. And that's because you have constructive interference. Okay. Now, these two protons are far enough that you're not getting a whole lot of constructive interference. You got to bring them in a little closer. All right. Now, what I'm going to do next is bring in the two protons, but we're going to look at the first excited state, the n equals 2 state, because the graphs are a little bit nicer. All right. That's all right. So make sure you have this. It's an exponential dip most of the way, and an exponential rise on the other side, and it's actually the sum. So it looks kind of like just a big U. Question, Andrew? The y-axis is an arbitrary scale. It's not arbitrary, but it's just I just want to have some whole numbers up there. In a quantum, if we did the full quantum treatment, there'd be like some Planck's constant, and the mass of the electron and stuff out there on that scale. So it'd be scientific notation out there, or maybe electron volts. But it's an energy scale. Or no, I'm sorry, that's a probability density scale. All right. So it can't be as high as 6. So because the probability has to add up to 1 for the, for this, if you calculate the probability across all these. So this is a bunch of different probabilities, but this is actually, if you calculate the entropy of this, did you ever do that, Andrew? If you calculate the entropy of this system, it's a lot higher entropy. That means that the hydrogen molecule has stored information, okay, in the form of its, and this is a covalent bond, by the way. Now, let's take a closer look at a covalent bond. Now, these two waveforms, as I said before, they represent probability distribution for a generic n equals 2 electrons. So that means it has 2 bumps, all right? The first bump is small, so don't worry about it. The big bump is the highest probability for seeing the electron. In other words, it's out there at the second energy level, all right? And when the atoms are far apart, their electron waves don't overlap. You don't really have much interference. So that's out here, all right? So I didn't draw the wave functions all the way out, but that's what they are, okay? So this is the first excited state. And you can tell this definitely looks different from Andrew and Brad's first excited state. That was just a bump and a dip. This is much more complicated, right? So this is for the two hydrogens far apart. They're not bound. You wouldn't consider them bound because they're both neutral. So they don't have an ionic bond or anything like that. But we can bring them in close enough to get a covalent bond, even though the system is still neutral. All right. Now here's how we do that. We just adjust the position of one of the atoms. So I'm going to bring in, actually I'm going to bring both of them in. Here we go. Oops, wrong direction. All right. When you bring the two atoms closer, their electron waves might overlap and you can get constructive interference. Okay, now here's the constructive interference right up here. Okay, that whole zone there. Okay, so that's like a rogue wave if we thought of this as ocean waves. Right? Now that's the highest probability of finding not one but two electrons. And so that's between, and notice this is a blue curve to represent the wave function of an electron. It's actually the wave function of two electrons. And you can see that there's a high probability of finding them there at that position, all right, relative to the other positions. So when you get constructive interference down there, and it's easy to see in n equals 2, now you're talking about at least constructive interference. And this is almost close enough for maximum constructive. You know, we could bring them a little closer, and you wouldn't even have a dip up there, all right? Well, we got a pretty big plateau with a little bit of a dip in it. You bring them a little closer, and yeah, you'll have a good peak up there. All right. Now, this is valence electrons cooperating or constructively interfering, and that's how you get a covalent bond. Now, all right, so make a sketch of that wave function. Now that's the wave function. To get the potential energy function, you square that curve, so multiply it by itself. In other words, get a little bit bigger central maximum, and then multiply it by V at each point along the scale. And so the maximum value of V times the square of the wave function is going to be here in the middle. All across here, you're going to have a good, all right? And then you do that, and what you find is, and you do that for the wave, for the electrons, but you also have, and you do it for the protons, okay? And the protons are, you do it for all 6 of the interactions. Use this wave function to calculate VAB, V12, VA1, VA2, VB1, VB2. You do those and you add them up, and this is what you get. And that, my wonderful students, is just like the classical curve. All right? And this one is calculated exactly. For H2, the internuclear separation is about 74 picometers. Okay, so that's 10 to the minus 12 meters. Okay, so about let's see, that's about 0.74 nanometers. Okay, and that's the bond length. That's where the system is stable. That's the covalent bond length. And so you can do this fancy calculation with wave functions, then look for the dip, and then you can measure, you know, in the chemistry lab, the bond length for the hydrogen atom, for the hydrogen molecule, and by God, it's right on the money. It's very, very close. All right. And we're always trying to see. Here's the classical profile. Look at that. There's the classical. Now it's a little different scale, but it's pretty close to this. All right. And this one's a little bit more. This one goes way up high. And this and here, Andrew, the energy, the vertical scale here, it's wave function squared times the potential energy. Okay, so the vertical scale here is energy. It's electron, and this one's electron volts. Okay, and so yeah, that's the potential energy. So that tells us that the hydrogen molecule H2, yeah, right about 74 picometers for the bond length. Here's another nice didactic curve. Okay, now here's one way to think about it. Down here at 74, yeah, that's your bond distance in the chem lab and also in your theoretical calculation, about minus 432 kilojoules per mole. Okay, so that's the typical chemistry nonsense of moles. Raise your hand if you love moles. Daniel, Tom, yeah, see some of the most unusual students just raised, but nobody else did. Anyways, moles. I actually understand moles now, but anyway, so look over here, right? Eyeballs and brains. Now over here where it says R equals 45, that means you've moved your protons into 45 picometers and then done your 5 squared times V calculation. And it's way up here, it's in the positive, and we've got a slope, very steep slope down and to the right. So what does that mean? That means you can't get a bond length of that size. They'll repel each other. This is where they like to be. Now out here on the right side, out here at R equals 300, R equals 150, R equals 150, they're weakly bound. That's a weakly bound H2. Out here, R equals 300, nah. They're going to want to repel each other. The H's are going to want to repel each other out at that distance. And that's what this graph tells you. And this graph is quantum mechanical. So my wonderful students, this thing that you've been calculating Monday and today, that classical model of the H2 molecule, the potential energy curve that you could get, it looks just like this. But this one is fully quantum mechanical. And it is lovely to behold. And that explains also how you get hydrogen to bond. Hydrogen's not going to want to bond. It's going to try to, it's either going to be free here, or it's going to be, they're going to be repelled. They're too close to repel. You can't. But right here, that's the sweet spot, 74 picometers, and the bond is because of quantum mechanics. All right, it's a stable bond, and you guys know the covalent bonds are pretty strong. Okay, I think you know that. Now, here's a picture of Linus Pauling, famous guy that figured out a lot of this stuff. And the question is, what distinguishes atoms that bond ionically from those that bond covalently? Well, here's the picture of Linus Pauling. He's famous for being an advocate of vitamin C. That's why he's holding the orange. He's also famous as one of the searchers for the structure of DNA, and he did a lot of the basic physics and chemistry to figure it out. Now, he didn't discover it. It was those other two guys that I never named. Rosalind Franklin's the one that bagged it, but that's supposed to be the DNA molecule. So let's talk about this idea. And here's something from one of his lab notebooks. It's kind of interesting. The properties of a bond between two atoms, which we were just talking about, are often determined mainly by one single electron wave function for each atom. And that's what we just did. And hydrogen molecule, there is only one electron anyways. But for other electrons like water, which is hydrogens and oxygen, yeah, you can do the same thing. And try to just look at that one valence electron and what it does, and don't worry about the other stuff. and you can understand a lot about bonding. All right, so, and what he came up with was this concept of electronegativity. Now, do you guys from chemistry class, do you remember that vocabulary word, electronegativity? Raise your hand if you remember that. All right, good. So that's good. So this is kind of review. It's basically colloquially known as the electron pulling power. Now let's take a look at this. This is a periodic table, except it doesn't have the atomic mass or anything, atomic number and all that, but it does have the electronegativity. So notice, first of all, no electronegativity numbers over here. No electron pulling powers for that column of the period. Now, why is that? It's noble. They don't like to bond. All right, so everything in that, the noble gases, they don't like to bond that much. All right, but we got other stuff that we could think of. Let's take a look at good old sodium over here. 0.9. That's a pretty low. If you look at this table, that's a fairly low value. All right, lower to the left and bottom, higher to the right and the top, except for helium in the helium column. Now let's take a look at chlorine over here. Nice, 3.0. And what do we know about those babies? What kind of bond are sodium and chlorine? Ionic. The chlorine stole Mr. Sodium's lonely electron. It's a lonely valence electron. It's outright theft. And that's encoded in the electronegativity. All right. So what you look at is the difference, delta, in the electronegativity. So in this case, it's 2.1. And we know that those babies are ionically bound. Okay, so those don't have, they're too far apart to have covalent bonding. You just have outright theft. So their attraction is not a covalent quantum effect, it's a classical ion effect. Okay, and it's a little bit weaker bond and stuff like that. You can calculate that. Now, so 2.1 for NaCl. Of course, that's good old table salt, salt of the earth. Now let's take a look at another compound. Let's take a look at oxygen. Yeah, 3.5. All right, so that's pretty good. It's almost as good as fluorine. Fluorine is the biggest one on the table, about 4.0. And here's carbon, right? 2 doors away, 2.5. That's fairly close. Now, carbon and oxygen form carbon dioxide, right? And that's a covalent bonding situation. And when you calculate delta for these two babies, you get 1.0, and that's considered a covalent bond. All right. So you calculate these wave functions, the single electron wave functions. You try to put them together, and you can figure out the electronegativity and then the bond type. Right. So the carbon dioxide, and you can figure out the different bonding types. Something from far on the left and far on the right is going to be ionic most of the time. Here's a table of the bond types. And, some people will say, well, I think it's actually greater than 2.0 for ionic, but, this is the one that I usually go with. Now, the middle variation is polar covalent. Now, the ionic bond is going to be polar. It's definitely a dipole. Polar covalent means that you've got a little bit more electron pulling power in one of your atoms. So it's not going to be, the constructive interference is not going to be symmetrically in between the two nuclei. It's going to be a little bit over to one side, so it's going to be polar. There's going to be a little polarity there. All right, and that polarity is very important, especially when it comes to water. Water is a polar molecule. And the covalent bonds in water are polar covalent bonds. And why is that? Because there's the delta is somewhere between 0.5 and 1.7, which you can look it up on the table. Calculate that out. From H to O is going to be a polar covalent. Now, up here we got NaCl. So there's another example. And for covalent bond, H2, and here's another example. CH4, that's methane. All right. And carbon likes to have 4, at least it likes to steal 4 or borrow for, or it likes to donate for. And it can go either way. All right. In this case, it's covalently borrowing or sharing the electron from each of the four hydrogens. All right. Now, polar water molecule. We'll talk about this for a minute. Polar water is considered the universal solvent because it has a lot of cool properties. Here's a diagram of it. We've seen this before. It's a polar molecule. The angles are 104, something like that, formed by the two, the two imaginary line segments from the center of the hydrogen to the center of the oxygen. All right. Now we know there's quantum waves floating around between there. One of the nice things about water molecules is it's polar, so you can get the hydrogen end of one water molecule to attract the oxygen end of another water molecule. And you'll have a fairly good bond there. That's called a hydrogen bond, right? And that hydrogen bond, what is it that happens when water bonds together? You get that hydrogen bonding. What do you get? Yeah, but what kind of a substance do you get? When a bunch of those babies, you get good solid hydrogen bonding. What do you call that? Polar, no, polar is kind of a vocabulary term related to what you get. What do you get from water molecules that bond together? Yeah, they use hydrogen bonds to bond together, a bunch of waters. So they don't form other molecules, it's a bunch of water molecules, they're still water, but they're bonded together by hydrogen bonding. And how do you get, what happens when you get a bunch of water molecules, H2Os, that bond together into, a strong, what? No, what do you get? Water? No, you get, well, yeah, you get liquid water, I mean, but what if what's the other thing that's really symmetric? See, you guys are from Florida, so you don't think in terms of it, but what do you get? Ice, snow. And how'd you guys go in there? Now, if we were up in Vermont, where I used to teach, everybody would, oh, yeah, Dr. B, that's snow. So write down for yourself, hydrogen bonding, water molecules, oddly, six-sided symmetry, snowflakes, etc. At a slightly higher temperature, that's only at cold temperatures where they really get tight. If it's a little bit higher temperature, you get cohesive forces, van der Waals forces. Okay, you get a droplet. Okay, so that's why liquid water. So Chris, you were right when you pointed to that water bottle. Okay, because that forms droplets. It's liquid water, and it's not bound in six hexagonal symmetry, but it is bound loosely so that when it's falling through the air, it'll be a round droplet. When it collects on the surface of your car, if it's waxed, you'll have round droplets. Okay, that's what that is. So that's hydrogen bonding. So quantum mechanics, covalent bonding, not ionic, leads to hydrogen bonding. That's intermolecular. And hydrogen bonding, also part of DNA. The backbone between now what do you call those? The guanines and the cytosines? Nucleotides, yeah. So that's hydrogen bonding. That's between those various amino acids. And then up the ladder, you got phosphates and stuff and I'm not an expert. I should hush my winkies, but yeah, you can see this diagram. Hydrogen bonds, the six what you call it, And you have deoxyribose sugar, and then you have the phosphate group, and blah, blah, blah. And that, my wonderful students, is all that I want to teach you for this semester. We'll finish with DNA, hydrogen bonding, which is covalent, which is quantum mechanical, but very, very easily understood in terms of the stuff that we started on the very first day. K Q1, Q2 over R squared. All right. Now, let me pause to let you think about the genetic code, and let me pause my